Hey guys, welcome back to another video. This video is getting into substitution and elimination reactions. This is chapter 10 in the book I'm looking at. So Sn1, Sn2, E1, E2, differentiating between all of those and deciding which one is the right one to take in synthesis problems is what this video is about. So first thing off the book, substitution is Sn2 and Sn1. That Sn is a dead giveaway that you're dealing with substitution. So just some basic things to think about. And elimination is E2 and E1. So when your professor says that, oh, you're doing E2, that means you're doing elimination that deals with a double bond and all of that. First of all, for substitution, Sn2 is dealing with a strong nucleophile. That NUC stands for nucleophile. So you're dealing with strong nucleophiles. So in the previous video that I looked at, where we looked at the difference between strong and weak nucleophiles, that's going to be crucial to deciding if you're doing Sn2 and Sn1. For Sn2, it primarily likes primary electrophiles. So again, I talked about what electrophiles are, those carbocations, those double bonded oxygens to carbons. You got the carbocation right here. You have the alkyl halides, which is that hydrocarbon chain into a halogen. So those type of things you want to be primary if you're dealing with Sn2. For Sn1, it deals with weak nucleophiles. So if it doesn't have a negative charge, more than likely that's going to be a weak nucleophile. And typically Sn1 deals with secondary and tertiary electrophiles. So this carbocation is a tertiary carbocation. So it'd like to go in Sn1. So if you need a refresher on strong and weak nucleophiles, this is a good picture. Remember, whenever you see, let's see, NaOH, that's the same thing as OH minus, because this is a spectator ion that sodium is, so you can just pluck that off, and that means that this is OH minus. So that you'll see a lot of NaOMe, stuff like that. That Na you can just pluck off if that helps you think about it. Substitutions means you substitute out the good leaving group for your nucleophile. So you talked about the common patterns in arrow pushing, and one of those was the loss of a leaving group. So you'll have a leaving group right here. Let's say we're doing Sn2 because this is a primary. This is a primary alkyl halide, and you're doing Sn2. You would just fit in whatever you have for your reagent in right here, because you're substituting out the good leaving group, and in this case that good leaving group is a halogen, in for whatever you have over that arrow. So that's substitution. And I have an example right here. Again, let's look at if it's primary, if it's secondary, if it's tertiary. So is this primary, secondary, tertiary? What is the reagent? And what do we do? So is this primary, secondary, or tertiary? This is a primary chlorine, because it's only attached to this one. That carbon is only attached to that chlorine, so this would be primary. So that deals with that first one. So if it's primary, we're dealing with an Sn2 synthesis. So this is an Sn2. Our reagent that we're looking at is a hydroxide. So you might also see this as NaOH. This is OH minus, so that is a strong nucleophile, strengthening our case for this being an Sn2 reaction. So our reagent likes to be Sn2. So what do? Just like I said before, we lose that leaving group and substitute in this OH group on that carbon. So how this will look on the product is this. Hopefully that makes sense. We'll move on to elimination. Elimination is different in a lot of ways than Sn or Sn2, Sn1, and substitution. You don't substitute in anything, you eliminate that leaving group and it leaves behind a double bond instead of, substituting something out into it. So these substitution and elimination words really give away what you're doing in your synthesis. So you're eliminating, as you can see in this example, you're eliminating that bromine, and in case of that bromine, you're dealing with that double bond. Okay. The one exception, so again, these double bonds typically show up on the more substituted carbon. So it either will show up on this carbon or this carbon when you, let's say I wanted to show the carbocation after I leave this, the good leaving group, you'll have a carbocation and you will look for the more substituted carbon for this reagent right here, because that's a strong nucleophile, strong base, and you have a tertiary alkyl halide. So you would want that double bond on the more substituted carbon, unless you're dealing with tert butoxide, and that's what this reagent is right here. That T stands for tert. Tert butyl, and then you have that oxygen that is bonded right here, and then you have this spectator ion, that potassium, that is T dash BO or BUOK, and it looks like this structure right here. And you would have that K plus as well. So when you have that, the major product for that will be the least substituted carbon. So just how I said with this example, we're dealing with the most substituted carbon. When you take off this good leaving group and you're left with the carbocation, it will choose this carbon instead because it's less substituted. And that's just the one thing that you'll have to know for organic chemistry. And it'll come up a lot in your synthesis problems. As I said right here, this reagent gives you a double bond on the least substituted carbon. Okay. So I have a diagram right here, and it's good to note that these things can happen in a variety of different ways. So we're dealing with nucleophiles, the strength of nucleophiles, and the strength of bases. And that really differentiates what kind of Sn1, Sn2, E1, E2 synthesis that you're doing, whether you get a double bond or whether you substitute out that halogen or whatever whatever is there. So this gives you, and feel free to screenshot this, or if you have a good one in your book, this gives you a good idea of the synthesis and the steps that you'll do. So in this first table right here, we have if you have a nucleophile only. So when you see, I have examples of nucleophile only. If you have a negative charge connected to a halogen or a sulfur, stuff like that, you're dealing with substitution. So you'll be substituting in that right there, and whatever whether you have a primary, secondary, or tertiary carbon, you're going to be doing substitution in one of those ways. For bases, the only two you really have to worry about, and the only two I saw, is this tert butoxide, which if you see that, it is always going to be a double bond. You're never going to be substituting a tert butoxide reagent. It's always going to be elimination. And if you have an H minus, that will also be a dead giveaway that you're doing elimination. Where it becomes complicated is when you're dealing with a strong nucleophile and a strong base. So for the examples I have here, if you have RO minus or you have OH minus, and again, this R means anything can be in that R. It really depends on if it's primary, secondary, or tertiary, what the major product is. And remember, the major product is it's more than 50% of the other product that's in there, and it would be the major residence product, you could say. So for primary, for a strong nucleophile, strong base, the Sn2 is going to be major, and you'll notice that unless you have one of these reagents where it's a base only, if you have a primary carbon, it's more than likely going to be Sn2, whether or not whatever base you're dealing with. But if you have a secondary or tertiary strong nucleophile and strong base on that reagent over those arrows, it's going to be E2. So it's going to be elimination. And this one, a weak nucleophile, weak base. So as we said, instead of like ETO, where that would be a strong base and strong nucleophile, if you add one of those hydrogens over it and it loses that negative charge, it's only going to work if you have high temperatures and if it's a tertiary a carbocation that you're dealing with. And you'll see Sn1 and E1. It won't just be specified as major and minor. So that's a really specific case, but that'll be an example as well. So this is another depiction of the 4 types of things you'll get if you want that as well. So let's go into an exercise. And this question asks to identify the mechanisms expected to operate when this reagent is treated with sodium hydroxide. So I'm actually going to give, the product it'll give off too, but we'll go through this kind of step by step. So the first step is determining if it's a primary, secondary, or tertiary carbon that it's attached to. And this one is tertiary. I'm sorry, this one is secondary. Whoops. It's attached to 2 other carbons right there. So it's secondary. So what does that mean? Well, we really have to look at the reagent and decide if it's strong or weak as a nucleophile or base. So this is NaOH, or it can be shown as OH minus. So if it helps to check back in your notes, OH minus is a strong nucleophile and strong base. So OH minus NaOH is a strong nucleophile and strong base. So that means, I'll write it out, strong nucleophile, oops. When you have a strong nucleophile, strong base, and it's secondary, you're doing E2, so you're eliminating it. So that means we need to get out that good leaving group and put a double bond in there. So you draw your arrow up to that bromine, and you end up with your product in the most substituted carbon, which you can choose either side. You can choose this side as well because they're both substituted the same, and you would get your answer. So this would be the answer for this problem. You're eliminating that bromine, and in place of that, you're putting that double bond in. What about this example? Predict the products for the following reaction. Identify the major and minor products. The minor product, which I didn't show, I just showed the major product. So this is the major product. If I wanted to add the minor, maybe you'll have that on your test. This would be the minor product, is substituting out that bromine in place of that hydroxide, or the alcohol group on top now. So that's the major versus minor. And I guess I'm doing major versus minor for this one as well. So what do we have here? We have another secondary, and we have OMe, which is a negative, because again, this is a spectator ion, so negatively charged oxygen. And what does that look like? That looks like OR minus, right? That R stands in place for that methyl group. So that is a strong nucleophile and a strong base. And we're dealing with a secondary carbon. So what would that be? That would be another elimination. E2 would be the major product. Again, we're not dealing with terp butoxide, so this would be a double bond on the more substituted carbon. So this is the major product. If I wanted to draw the minor, all you would have to do, you're going to realize that substitution is very straightforward. And you're just adding that OMe, and that's the minor product. And why I draw a wedge is because usually when you have substitution, the regiochemistry, that's stereochemistry. The stereochemistry, when it's a wedge and it goes through substitution, it'll end up as a dash, but in this case, it started as a dash and ends as a wedge. So we have another major elimination for this problem. What about this problem? I have the same reagent, so this is, we just dealt with this reagent, so we know it's a strong nucleophile. We know it's a strong base as well. So it really depends if it's 1, 2, or 3 to determine if it's E2 or Sn2. Okay. So are we doing elimination or substitution for this reaction? Well, we have a primary carbon right there. It's only attached to one other carbon. So if it's primary, we are doing Sn2. So we have a strong base and strong nucleophile, so we know it could be both. So our major product will be Sn2. So that OMe will replace that chlorine, and that's our major product. Our minor product, we're just looking for the more substituted carbon. There's only really one carbon you can put on there because of how this works. So you'd end up with a double bond right there. Obviously that's not the most substituted, but since this is primary, you can't really rearrange it. And that would be the minor product. You wouldn't even really see this. You would only be shown the major product. Usually when I see exams and tests, it only shows for these primary ones to show the major product, because that just looks awkward, that minor product. All right, so this is a good diagram of what you'll see with substitution and elimination and the different reagents. I highlighted here the ones that I didn't share yet. Well, I already shared the terp butoxide, and that's you're substituting in on the least substituted carbon. But another one that you'll see is this TSCl with pyridine. You can see that comma pyridine, and that changes an alcohol, which is a bad leaving group. That changes it into a good leaving group. And that can completely change whether you're doing substitution or elimination. Because we know you want to do Sn1 if you're dealing with a bad leaving group or you have a weak nucleophile. But if we can change our leaving group to a good nucleophile, it can change what kind of synthesis we do, whether that's Sn1, Sn2, or E1, E2, stuff like that. All these other ones you guys have seen before. And it might be hard to know that, but this is all substitution. So we're just substituting in this CN, we're substituting in this carboxylic acid. You can see we added a methyl at the end here, and we added 2 carbons and another hydrogen. So we added everything in there, and even though this looks scary, you guys you're gonna all see these problems. And if you're wondering how to get back your good leaving group to your alcohol group, it's just a substitution again. All right, and I guess one more that you haven't seen is this HBr going from the alcohol into that alkyl halide. It's just using HBr. All right, one more here is stuff that you haven't seen is this one, this concentrated H2SO4. That's another elimination reagent that you can use to get the most substituted. So this would give you the most substituted carbon. So instead of using a halide, a halogen, we're using alcohol to go to a double bond. So that's the one change that's shown there. And that's because it's a bad leaving group, so we have to use a different reagent than just NaOH that we can use for this good leaving group. All right, so that wraps up this video. In next video, I'm going to go through a lot of practice problems on Sn1, Sn2, E1, E2 substitution and elimination problems. So you can check out the next video if you want more practice problems.